In first year calculus, we studied functions with one input and one output. In studying curves in 3D space, we were essentially studying functions with one input, but now 3 outputs. And what we found in that case was that we could mostly just work with all the component functions individually. But there's lots of things that are going to depend on more than just one input. For example, if we have a cylinder, the volume of a cylinder depends on the radius of the base and the height of the cylinder. So V equals pi r squared h. Depends on r and h. Or kinetic energy in physics is equal to 1/2 mv squared. So here m is mass and v is speed. So we'll write Rn is the set of all tuples of n, ordered tuples of n real numbers. So each xi is a real number. For example, R3 is the set of all triples of real numbers, so this 3D space that we've been working with. And I'm going to sort of stop being pedantic about the difference between points and vectors from now on. So we want to study functions which take in n inputs and one output. So we'll write this often as w equals f x1 xn. So these we call the input variables, and this we call the output variable. So for example, I'm going to have f of x1, x2, x3, x4 is x1 squared plus x2 squared is x3 squared plus x4 squared. Or f of x, y, z, let's call these x1, x2, x3 is x1, x2 squared, x3. You can think of this as either a function of n real number variables, or a function of one vector variable, so n-dimensional vector variable. Of course, these are the same thing, but somehow conceptually, the latter way just seems like it's less data, sort of hiding some complexity away. It would also be natural to consider functions with multiple inputs and multiple outputs, so to put Rm over here. But as we saw with curves, erase some of this. As with curves, that would just end up giving us like W1 is F1, X1 through Xn through Wm is Fm of x1 through xn. So we can treat these these output variables all independently. Or maybe a clearer way to say this is if we have one function from Rn to Rm, this is the same as m functions from Rn to R. So one function with n inputs and m outputs is the same as m functions with n inputs and one output. But you can't do that, so one function Rn to R is not the same as n functions from R to R. So this does not work. Like you can't, because these variables, input variables, can interact with each other. Okay, so just as in 3D, with three input variables, we want to think of these geometrically. So for example, let's go back to these two equations. V, volume is pi r squared h, or kinetic energy is 1/2 mv squared. Now these seemingly are describing different situations. This is cylinder, this is about some object that's moving. But we could visualize both of these using the equation z equals 1/2 x y squared. So in the first example, r would correspond to the variable y, and h would correspond to the variable x. And in the second example, m would correspond to the variable x, and y would correspond to the speed. There's different constants like on the first one, but that doesn't matter so much. So the geometry of that shape over here encodes the relation between volume, radius, and height, and also between kinetic energy, mass, and speed. Now, how do we visualize in higher dimensions? So there's a few answers to this. One is to visualize 3D space and then just say in your head n, or for a particular value of n, like say 7. Now you're visualizing 7-dimensional space. Another way is that, for example, 1 point in 6D space is the same thing as 2 points in 3D space. And often that's like how it would come to you. Or 3 points in 2D space. So in this course, we're mostly going to, I guess I want to leave those other equations up. We'll mostly stick to (2D) and 3D, partly for concreteness, partly because this already covers a lot of the applications and examples that are relevant. But everything we'll do can be done in n dimensions. And like it's valuable to do so, even though n-dimensional space doesn't physically exist. There's lots of situations where we have more than 3 inputs, and we would like to still think about that using spatial intuition. Everything except for a couple things about the cross product. This is something slightly amazingly that only works in 3D space. All right, so next, often it'll be the case that a function may not always be defined on all. No, it's not always defined on all Rn. For example, we took f of x, y, z is 1 over x squared plus y squared plus z squared. This is not defined at 0, 0, 0, since we can't divide by 0. So we call the domain of a function is the set of all acceptable inputs, which generally means can't divide by 0, can't take square root of a negative number, because we don't want to introduce complex numbers, and can't take ln of something less than or equal to 0. Then the range is all the possible outputs. So just as for functions of one variable and one output. The range may or may not be, is not always easy to determine the range. In this example, we can see that the range is 0, infinity. This will always be, since x squared plus y squared plus z squared is always greater than 0, this will always be greater than 0, and we can hit every positive real number with this function. So now let me do a few more examples. For instance, let's find the domains of these 3 functions and then sketch those domains. So for f, we can't divide by 0, so we need x minus y squared not equal to 0 and y minus x cubed not equal to 0. So the domain is going to be R2 minus xy such that x equals y squared or y equals x cubed. So a picture of that is, so this is like R2, then the curves x equals y squared, that would be this, and the curve y equals x cubed will be this. So the domain is everything except for these 2 red curves. Then for G, I'll erase this So for G, we can't take the square root of a negative. So we need x squared minus 25, y squared minus 9 to be greater than or equal to 0. Now this can happen one of two ways. Either x squared minus 25 is greater than or equal to 0, and y squared minus 9 is greater than or equal to 0, or x squared minus 25 is less than or equal to 0, and y squared minus 9 is also less than or equal to 0. So either they're both positive or both negative, or both non-negative or both non-positive. So this is this x squared greater than 25. These all become x squared greater than or equal to 25, 9. And now if we take the square root, this will become absolute value. So this is saying that absolute value of x is less than 5. Absolute value of y is less than or equal to 9. Less than or equal to 3. And the same over here. So this translates to absolute value x greater than or equal to 5 and absolute value y greater than or equal to 3. So let's trace that out. So the axes are just going to indicate, the blue is just indicating the axes. Now the domain, so x greater than, let's draw 5 and negative 5 here, and 3 and negative 3 here. So the first region, absolute value of x greater than or equal to 5, and absolute value of y greater than or equal to 3, that will give us this, and this, and this. Then the second region will give us, so x less than or equal to 5, absolute value of x less than or equal to 5, and absolute value of y less than or equal to 3. So that will be this region. So the domain is the union of all of these green parts. All right, now let's do finally h. So for h, x, y, we can't take ln of a negative, of a non-positive, and we also can't divide by 0. So first, so we need x squared plus y squared to be greater than 4. So in the plane, that's saying that, so if this is a circle of radius 2, then we are not allowed to like beyond this, but everything outside of here is allowed. And then we also are not allowed to have x squared plus y squared minus 4, this cannot equal 1, or else we would, ln of that is 0, and then we would be dividing by 0. So x squared plus y squared also cannot be equal to 5. So x squared plus y squared is not equal to 5. So you redraw this. So I'll draw in red everything that's not in the domain. So in red, we're not allowed to have x squared plus y squared less than equal 4. So this is a circle of closed disk of radius 2. But then also, we are also removing a circle of radius square root 5 from the domain.